In this lecture, we're going to discuss acids and bases, and we're going to start off with a few different definitions and different types. So first, we're going to talk about Arrhenius acids and bases, and there are really three different types of acids and bases, and they all are based off of different kind of ideas and what is being considered an acid or a base. So the first one is the Arrhenius acid and base, and we're talking about an acid as something that creates hydrogen ions in water. And a lot of times you'll actually see this written out as H3O, and this is the same thing as just having an H plus written out. If it's in water, typically hydrogen or protons are not going to be just floating around freely. They'll actually attach themselves to H2O, and then you'll see here we add that extra hydrogen, and then we actually have H3O. So when we're in water, typically the H plus ion is going to be associated with a water molecule. Now, when we're talking about bases for the Arrhenius equation, or the Arrhenius acid or base, we're looking at bases. We're talking about producing hydroxide ion, OH ion. And when we combine these two acids and bases, we're going to make water and a salt. So you'll notice that if we have HCl and sodium hydroxide, we'll generate water and a salt. And we've practiced doing some of this before, where we'll break those apart, where those are non-metals, so they'll break apart. This is a polyatomic that'll break apart into sodium plus an OH minus. So this is our acid is going to produce that H plus, and our base is going to produce the OH minus. So this is the base over here. And then you can see what happens again when we talk about H plus. We'll technically be generating H3O plus instead of just the H plus. So you can see that drawn out here or written out there. We have chloride ion, sodium ion, hydroxide ion, and we swap partners so that we'll kind of add that positive proton to that negative OH. Will generate the water, and then we still have our salts as spectator ions in this solution. Another term that I'd like you to know is the idea of this amphoteric substance, and that's where it can act as either an acid or a base. So it can be either a molecule or an ion, and an example of this would be hydrogen carbonate. So if we're looking at the form of an acid, we have H3O, HCO3 minus, and OH minus. And then, so we're able to create water and a salt, so it can act as an acid, or it can act as a base by taking on that proton from an H3O plus, and we're still generating a salt and water here. So there are situations where we're going to have something that is going to be able to donate or accept a proton. And so this can be subtle, but it's an important difference in terms of these types of substances. When we get into organic compounds, there are a lot of substances that can be amphoteric, where they would be able to take on a proton or release a proton. And we'll talk about how we decide which of those things are going to happen. The next type of acid and base I want to look at is the Bronsted-Lowry definition of an acid and a base. So if we're looking at, for example, we have acids and bases, you can see different sets of these acids and bases. And here, Bronsted-Lowry acids have to contain a proton, whereas Bronsted-Lowry bases must contain a lone pair of electrons that it can use to attach to a proton, for example. So here are all examples of Bronsted-Lowry acids, and you'll notice that they all have hydrogen elements on them that will be able to be donated. And here we have Bronsted-Lowry bases. They all have lone pairs. So oxygen, nitrogen are some examples there. I should point out that also, in addition to lone pairs, pi bond electrons, or double bonded or triple bonded electrons, these elements can also act as Bronsted-Lowry bases. So anytime you have a double bond, you could also use those in acid-base reactions. In this next example, I'd like you to annotate the different acids and bases and just take a moment to identify those. And what you'll be able to notice pretty quickly as you do this, you'll be able to identify most of the acids. You'll be able to identify the acids here in red. And typically these are better acids because they're attached to more electronegative elements. They'll be able to be released pretty effectively. And we also have all of the base elements identified as well from the lone pairs of electrons. And then we also have the pi orbitals. So these are all different potential Bronsted-Lowry bases in blue. So I'd like you to look at this learning check looking at Bronsted-Lowry acids or bases. We have A, B, and C. Which of these compounds would be Bronsted-Lowry acids in the top three, and which would be bases in the middle three, and then classify the compounds as acid, base, or both for those bottom three, and post those in our Blackboard space. Before we get too far into these different mechanisms and the different types of acids and bases, I do want to go over a certain technique that is used to demonstrate where these electrons are going to be going and coming from. So in organic chemistry, it's really important that we look at where electrons are moving, not necessarily where protons are moving. So you might have to unlearn some things to do this. A lot of times people want to draw arrows to where the protons are going or the positively charged compounds are going, and that's not, we're not going to really move those. We do move electrons, move a lot more easily. So what you can see here is this is called curve arrow formalism, and we're going to show the movement of electrons. So you can see here that we have a double bond, and we spoke earlier that those double bond electrons, those can move and they can rearrange themselves. And we have a lone pair in nitrogen up on top. So this arrow that's coming out of the two electrons on top of nitrogen that's negatively charged, those are going to move in between the nitrogen and the carbon, and then they're going to form this new bond that's shown here on the other side of that double arrow. That double arrow is telling us that these things can kind of go back and forth between these two compounds. Now we have this, and I'll give this a different color just so we can kind of see where those are going. I'm going to give this bond a blue color, and those are going to be now those blue electrons on top. So you can see that the arrow formalism is showing us where those electrons are going to go. And we use two-sided arrows. If we have two of those kind of sides on the arrow, that means both of the electrons are moving to that spot. And you can see from the lone pair of the nitrogen between that carbon and the nitrogen, both of those electrons, because we have the double arrow, those are going to be forming that double bond. So remember, when we're doing this, the base of the arrow should always start with the electrons that are moving, and then we're going to point to where they go. A lot of times they're going to point towards positive or partial positive charge. If we look closely at this first example here, we'll actually should be able to recognize that this carbon is going to be partially positive because we have more electronegative elements of that oxygen is going to be more electronegative, and that's going to help direct where these electrons are going to be going. So you can see that the negative electrons are going to kind of go towards that positive center, and then that's going to force these other electrons in the double bond up towards the oxygen. So I'd like to show you a couple more of examples of how we can do this and use arrow formalism to show where electrons are moving. So now on this top part we have an H3O. We can see that H3O plus positively charged and an OH minus. And we're going to make two H2Os. Sometimes I like to make two H2Os as HOH, because that's really what's happening here is we have the polyatomic OH and the proton coming together, and that's going to equal H2O. But when we're looking at these, sometimes it's easier to kind of see what's happening when we draw it out as an HOH group. So here what we're going to have to do is, if we're looking at this top equation, we know that we want to generate 2 water molecules out. And that means we have to add a proton to the compound on the right, and we have to remove a proton from the compound on the left. So how do we do that? We're going to have to grab a proton with the hydroxide group somehow. And what we're going to want to do is we're going to use these lone pair. And remember, we start, if we're doing arrow formalism, we start the base of our arrow is going to start there. And I'm going to grab the closest proton that I can find, which happens to be that one. And now if I were done, then we're going to make a bond between the oxygen and the proton. So if I just finished here, that would mean that we'd have a hydrogen attached to an oxygen, a proton, another oxygen, another proton. Well, we don't want that whole big thing as one group. We need 2 separate sets of groups. So we're going to have to release those electrons in that bond and give them to the oxygen so that we have the H2O compound is by itself. So this will then give us the H2O with this group, and then we have another H2O with that group, and then we'll have this compound on the right side of the arrow. Now let's look at this other example, and what we want to do is, it's helpful to look at the difference before and after. So we go from NH3 to an NH4 plus. We have a carbon-carbon oxygen hydrogen double bonded to an oxygen here in that carbonyl group. And then all of a sudden that group is now a negatively charged oxygen instead. So how do we do that? We're going to have to get rid of this double bond in the carbonyl double bond, and this ammonium group, this amine group, is going to have to become ammonium. So we're going to have an ion form. So that group is going to be our base, because it's going to have to grab different types of, it's going to have to grab a proton. We'll also notice that this group from an alcohol turns into a ketone. So we're going to have to do something with that. So let's look at what we can do. So we can take that arrow and point it down to that proton. And then we're going to use this bond now that those electrons are going to move between that carbon and the oxygen. The problem now is that we would have too many bonds to carbon, so we'll have to move those electrons as well, and that will give us our final product. So we're going to walk through this a little more slowly when we're talking about acid and base reactions, but I do want you to see how these things can move in order to kind of see what is going to be created here and how we can generate some of these different compounds through this arrow formalism. Okay, so let's look at this arrow formalism in relationship to acid-base reactions a little more closely here. So if we're looking at a Bronsted-Lowry reaction, we're talking about a base that has a lone pair of electrons or a pi pair of electrons, right, from a double bond. And in this case, we're just showing you a lone pair example. And then we have a proton that can be used as something that lone pair is going to be attracted to. So here we have an acid and a base on the left and the right. And we're going to use that. Remember, the arrows draw from the lone pair of electrons that are shown here, and they're going to point towards that proton. Now, typically, not always, but usually, there's going to be some type of electronegativity difference between these two. So you can think of these as negatively charged center, and we're going to be pointing towards a positively charged center. And that is typically how we're going to arrange those. And in order to break that bond between the proton and the other compound it's attached to, we have to draw those arrows away as well from that bond, and they're going to be moved towards that adjacent element. So here we have that in the middle, a double arrow is saying that this reaction can really go both ways. It's not just a one direction reaction. The acid and base can fall apart and come back together. Once we kind of get to the other side of this arrow, there are two new terms now. So the acid turns into the conjugate base, and the base is going to turn into the conjugate acid. So you'll notice that that base center now has that proton on it, and theoretically that proton can fall back apart. So let's look at the arrow formalism for that. We would have this being attracted to that proton, and then the electrons in that bond would go back to the base. So that would give us this arrow going backwards. So that is the idea between a Bronsted-Lowry acid and base chemical reaction, looking at these arrows. So what we're going to do is we're going to have to be able to identify the conjugate base, identify the conjugate acid, identify the acid and the base in these chemical reactions to figure out what's happening and which direction these reactions are going to flow. So I'd like you to take a look at these two different chemical reactions. First step is to be able to identify the acids and the bases. So we have the base here is going to be looking at that nitrogen. How do we know if I'm giving you the full chemical reaction? We can look over here at this other compound, and the nitrogen now is attached to another proton. So that has to then be the conjugate acid because we've added a proton to that base. So these are connected to each other through that chemical reaction. And we know then that the other compound, the acid, is going to turn into the conjugate base. So these are relationships that you're going to need to be able to know for some of the stuff that we're going to do coming up here. Now the next part is this arrow formalism we have from those two electrons on the nitrogen. We're going to grab that proton, be attracted to that, and that bond needs to break, and we have to show where those electrons are going to go. They're going to go towards that oxygen. So you can see that oxygen now has a negative charge because it's attracted those two electrons, and our conjugate acid now has 3 hydrogens attached to it rather than the 2 it had on the left side. So that's one type of acid-base reaction. Now let's look at the second example, the one below. We have lone pairs of electrons in the oxygen. They're going to be attracted to that proton on the chlorine, and that chloride ion is going to form by taking those 2 electrons in that bond. So this is our now conjugate base. We have the acid loses the proton and turns into the base, and then our base gains a proton and then turns into, again, that conjugate acid. And now we have this oxygen is attached to 2 hydrogen ions, and we have a positive charge on that. So the other thing to make sure of is that if your charge on the left is neutral, then your charge on the right needs to be neutral. If the charge on the left is negative, the overall charge on the right needs to be negative. So we'll notice that we have a negative charge on that nitrogen on the top reaction, and that charge is still there. So overall, we have a -1 charge on the left side of the arrows and a -1 charge on the right side. With the reaction below it, we'll notice that there's no charge on the left side, so there's an overall net charge of 0. And on the right side, since we have a -1 plus a +1, we have a no net charge as well on the right side. So we'll be able to have that same charge has to be on the left and right. And if we change the charge on the left to the right, that would mean that we created or destroyed an electron, and we can't do that in chemistry. That's conservation of mass, conservation of matter, so we can't do those types of reactions where those disappear and go away. So remember to make sure that those are accounted for. All right, so for this one, I would like you to be able to work through these problems. So there are 3 problems below that I would like you to identify the acid, identify the base, identify the conjugate base, and identify the conjugate acid. So this is the first step for doing these chemical reactions. And I'll do the first one with you, and I'll kind of show you how I walk through this. So I know that we have an HClO2 and then we go to a ClO-2, and that means that this lost a proton. So if I lost the proton, this must be my acid, because again, it's donating a proton through our definition. So HClO2, that's going to be my acid. And if it now lost that, that now must turn into my conjugate base. So I'm going to draw that compound out. So that's my conjugate base. So by default, the H2O on this side of the arrow has to be my base. And then the H3O plus must be my conjugate acid. So this is the first step in being able to do some of these chemical reactions and doing this arrow formalism, is to kind of come up and be able to identify the acid, the base, conjugate base, and the conjugate acid. So please do these other two reactions and post those in our Blackboard space. So here's another example of where now we're going to kind of layer what I'm asking you to do. So first of all, I want you to identify the acid and base and the conjugate acid and conjugate bases. And then I want you to use arrow formalism to show those lone pair of electrons in the base attacking that acid. So I'm going to do B for you because it's a little tricky, because we're kind of missing something that isn't being drawn out. So there's an assumed hydrogen here, right? There are actually 3 hydrogens that are attached to that carbon on the end that weren't drawn in and typically are not always going to be. But since it's part of the chemical reaction, sometimes it's nice to have. I know that that is actually losing a proton, because I can see over here on the right side that that proton went away, and now we have a lone pair of electrons on that carbon. So what I need to have done is I'm going to have to draw an arrow from that oxygen, and we know it has gained a proton, and these electrons are going to bump off onto that carbon. So that's how we would draw the arrow formalism. Now, based off of this, I know that this is our acid because we're losing a proton here, and this then must be the base because we're gaining a proton and we're also donating a lone pair of electrons. That means that this is my conjugate base, because that's what your acid turns into after it loses the proton, and this is the conjugate acid, and because it has gained that proton on the end. So this is how we would draw the arrow formalism and identify these different compounds. So I would like you to do this for A and post that answer in our Blackboard space. All right, some more practice for your understanding of acids and bases. So I want you to draw the conjugate acids of each of the following for A and the conjugate bases for the acids listed in B. So for A, we're going to add a hydrogen. So if we're looking at, for example, the first group, NH3, we're going to add a proton plus H+, then that is going to give us an NH4 plus charge. That is going to now be our conjugate acid. So that's this one here. So I'd like you to do these other two and post those on Blackboard. For B, drawing the conjugate base, I'll look at HBr. You do the other two. If we're going to do HBr, we know that we are going to draw the conjugate base of the acid. We're going to lose that proton, right? So we're going to give the electrons in that bond to the bromine. So that's going to be a Br minus, and that H plus is going to go away. So here is an example of what would be the conjugate base for our initial acid. All right, do these other two and then post those in Blackboard, and let me know if you have any questions about that.